Good morning, my dear students. In our previous video lecture, we discussed about a very important Gauss law and some of the important applications of Gauss law in order to find out electric field intensity due to various type of charge distribution. Okay, so far those who have not seen my previous video, they can go to YouTube search and they should type Gauss law by Swapnil, Sajane. You are going to get a detailed information about Gauss law, Gaussian surface, and some of the important applications of Gauss law. Okay, and in today's discussion we are going to discuss one more important application of Gauss law, and that is electric field intensity due to uniformly charged thin spherical shell, or you can call it as hollow sphere also. Okay, so for this case I have considered a hollow sphere whose radius is R and center O. Okay, since it is a conducting sphere, due to repulsion, all these positive charges are located on the outer surface of the conductor. Okay, beyond the outer surface they cannot move because there will be air, and air is what? Insulator. Therefore, these charges wish to locate on the outer surface of the conductor due to repulsion. Okay, and for this case we shall consider three different cases. Okay, so one case is on the outside. Point P is outside the sphere and on the surface of the sphere and within the conductor. Okay, within the sphere. These three cases we shall discuss, and on all those points, okay, outside, on the surface, inside, we shall calculate electric field with the help of Gauss law. Okay, so let us start by first case, that is point P outside the sphere. Point P outside the sphere. So first point, we are supposed to consider a Gaussian surface, and conditions for Gaussian surfaces are the angle between electric field intensity and area vector has to remain throughout the surface. Okay, or electric field has to be symmetric, that is the point, or R distance has to remain constant. Okay, these are the conditions in order to consider Gaussian surface. Let point P be located at a distance of R from the center of the shell. Okay, and for this case we shall consider a Gaussian surface. Since it is shell, we shall consider Gaussian surface in the form of sphere. In the form of sphere, and radius has to be R, with radius R and center O. My dear students, please observe here. If I consider a hollow sphere, sphere, Gaussian surface in the form of sphere, okay, with radius R, you can observe for this conducting sphere and Gaussian surface, both have same center O. Okay, for this we can call it as concentric also. See here, this is Gaussian surface actually. Okay, so this is Gaussian surface. Imaginary surface actually it is. It is not a real surface, imaginary surface. And this Gaussian surface has a radius how much? R. And this conducting sphere has the radius how much? R. Okay, so this is Gaussian surface, concentric. Okay, so at point P we are supposed to calculate electric field. As these charges on the conducting shell are positive charges, the direction of positive charge will be outward like this. So these are the direction of electric field lines like this. Okay, and as you can observe, all these positive charges radially outward direction, they appear to be coming from center. Okay, like this. They appear to be coming from a single charge located at the center. Okay. Okay, so we shall calculate from Gauss law closed integral E ds is equal to Q divided by epsilon naught. Okay, so LHS part is closed integral E ds is equal to closed integral E ds theta cos theta, and theta is angle between E and ds, cos theta. See, you can observe here, this is Gaussian surface actually, Gaussian surface. We shall consider a very small area, let us call it as ds. Okay, so ds is small surface area of Gaussian surface, and for this small surface the area vector will be perpendicular to the surface. So this is ds, sorry, this is area vector, and this is what? This is electric field. You can observe the electric field intensity and area vector, they are in same direction. The angle between these two is how much? It is 0 degree. If I consider this electric field line, okay, and the surface area will be ds, very small surface, and area vector will be a, and the angle between electric field intensity and area vector, once again it is how much? It is 0 degree. If I consider this line, I mean this line of electric field, once again ds will be outward, I mean normal to the surface, and the electric field is also outward. It means the electric field intensity and area vector, they are in same line, therefore angle is how much? 0. If I consider any point, the direction of electric field intensity and area vector, it is going to be 0 degree, because both are perpendicular to the surface. Okay, therefore here theta value is how much? 0 degree. So closed integral E ds is equal to, it is 0 degree, and electric field is a constant, it is taken outside, closed integral ds. See here, if I add all the ds's, see, this is ds, 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 ds. If I add all these ds's, I am going to get total surface of the Gaussian. Understood? Therefore, and this is in the form of what shape? Sphere. And surface area of sphere is how much? It is 4 pi r square. R is radius. So let us call it as equation. Okay, it is equation number 1, and it is equation number 2. Okay, and RHS part, charge within the Gaussian surface, because Gaussian surface is charge within the surface, we are supposed to find out charge within the surface. Which surface? Gaussian surface. Okay, there are many charges actually, but all those charges, if I observe from this location, they appear to be coming from center. Okay, therefore it is Q divided by epsilon naught, because all these charges, many charges are there, but all those many charges appear to be coming from what? From the center. Okay, appears to be coming from center. You can call it as point charge. Okay, therefore it is Q divided by epsilon naught. Let us call it as equation 3. From 2 and 3 in 1, substituting equation 2 and 3 in 1, we are going to get E into 4 pi r square is equal to Q divided by epsilon naught, or E is equal to 1 divided by 4 pi epsilon naught Q divided by r square. See, this formula exactly looks like electric field intensity due to point charges. Okay, see, there are many charges located on the outer surface of the conducting sphere, but as if we observe the directions of electric field lines, the electric field lines, they appear to be coming from center. Okay, as if there is one charge located at the center and the direction is radially outward. This is how it actually looks like. Okay, Therefore, formula is to be E is equal to 1 by 4 pi epsilon naught Q divided by R square. This is point P on the outer surface of the shell. And second case, point P on the surface of the sphere. I will write here only. See here, second case, point P on the surface. P on the surface of shell. If I consider point P on the surface of the shell, then radius of the conducting sphere and point P distance both are going to be same. Okay, see here you can observe. Therefore, R is equal to R. Therefore, formula is going to be E is equal to 1 divided by 4 pi epsilon naught Q divided by R square. Okay, and see here, if I consider point P on the surface of the shell, okay, so many charges are located on the outer surface of shell. Okay, and actually this is surface, and for surface charge distribution we have defined one term, and that term is sigma. What is sigma? It is a surface charge density. Surface charge density. And surface charge density, since there are many charges, the total charge is going to be Q is equal to sigma into A. What is A? A is area of this surface. Okay. And area of this surface is how much? It is 4 pi R square. So sigma 4 pi R square. Okay. Or you can write capital R also, because both are same. So I will write here 1 divided by 4 pi epsilon naught Q. Q is equal to what? Sigma into 4 pi R square divided by R square. So 4 pi is cancelled, R square is cancelled. What is remaining? I will write here E is equal to sigma divided by epsilon naught. This is what remaining. So this is electric field intensity on the surface of the charged spherical shell, conducting shell. Okay. This is second case. And now we shall go for third case. Third case, point P inside the shell. See, for this we shall consider once again conducting shell. The radius of conducting shell is R. And if I consider a point P inside the shell, it is point P. And for point P, I have to consider one Gaussian surface. I will consider another sphere, and the radius is going to be R, because this point P is located inside the shell. Therefore, I am supposed to find out electric field intensity at point P, okay, at a distance of small r. As you can observe, all the charges are located on the outer surface of the conducting shell. Therefore, there are no charges within the Gaussian surface. Within the Gaussian surface, there are no charges only. Therefore, from Gauss law, closed integral E ds is equal to Q divided by epsilon. Q is what? Number of charges enclosed by the Gaussian surface, and there are no charges. Therefore, charge is equal to 0. 0 divided by anything is 0. Therefore, closed integral E ds is equal to how much? 0. ds can never be 0. Therefore, electric field is equal to 0. It means electric field intensity within the conducting shell is how much? It is 0. It is very important case. Why electric field intensity within the conducting sphere is 0? Because there are no charges. Charge only constitute electric field. Therefore, there are no charges within the conducting shell. Therefore, electric field intensity within the shell is 0. Okay. So, 3 different cases we studied actually. This is electric field intensity outside the shell. This is on the surface of the shell and this is within the shell. Okay. I will rewrite here. First case, E is equal to 1 divided by 4 pi epsilon naught Q divided by R square. This is outside. And second case, E is equal to sigma divided by epsilon naught. This is on surface. On surface. And third case, E is equal to 0 within shell. Okay. By using all these three cases, okay, we shall draw a graph, okay, between electric field intensity and distance. What happens if distance increases or decreases? See here. Graph electric field intensity versus R. It means electric field intensity with distance. This is electric field intensity and this is distance. As you can observe here, inside the shell there is no electric field. Therefore, if I consider this distance as a radius, okay, it is inside. Inside electric field is how much? 0. Till what point the electric field intensity is 0? Till at distance R. Okay, electric field intensity is 0. And at R, okay, at R distance the electric field intensity is maximum. At this location electric field intensity is maximum. This is max case. Maximum electric field intensity. And as you walk away, as you go away from this point, okay, from the outside, from the surface of the shell, electric field intensity go on decreasing. Therefore, outside electric field intensity go on decreasing like this. Okay. So this is E max, and it is inside. Sorry. Outside. E is inversely proportional to square of distance. Okay. So this is graphical representation of electric field intensity and distance. Okay. E is 0. Okay, this was case of conducting hollow sphere. If we consider a solid sphere, then we shall calculate electric field intensity. Okay, so let us discuss electric field intensity for solid sphere. This was for hollow sphere, and now we shall check for solid sphere. Solid sphere. It is actually non-conducting. For this, once again we shall consider a solid sphere. Okay, if it is solid sphere, all the charges will locate inside the sphere only. They do not come outside or on the surface of the sphere. It is non-conducting actually. Non-conducting. So charges locate inside only. So once again we shall consider point P outside the shell, on the surface of the shell and within the shell. So this is center O, and this solid sphere has a radius how much? R. And let us consider one point P outside the sphere. So at this point, that is first case, outside solid shell. Electric field E is equal to, according to Gauss law actually, closed integral E ds is equal to q divided by epsilon naught. But if you observe from this location, what you observe is this shell, okay, filled with so many positive charges, the direction appears to be radially outward, okay, as if at center one charge is located, point charge is located, and the direction is radially outward. This is how actually looks like, okay. Therefore I can directly write it as electric field E is equal to 1 divided by 4 pi epsilon naught q divided by r square. This is electric field on the outer surface of the shell, solid shell, okay. And second case I will write here, on the surface of shell, that is r is equal to r. See, if this is shell, then this is radius r and this is point p, okay. Then electric field E is going to be 1 divided by 4 pi epsilon naught q divided by r square. Now the third case is point P within the shell. Point P within the shell. Actually non-conducting shell it is, okay. For this we shall consider one shell, okay, and the radius of the shell is r, and this shell is filled with positive charges, okay, and let O be the center of this shell, okay. Now let us consider one point. This is a point, let us call it as P, and this point P is at a distance of r from center of the shell, okay. And at point P we are supposed to find out electric field intensity. In order to find out electric field intensity at point P, we shall draw a Gaussian surface in the shape of another shell, this way, okay. And this radius of the Gaussian surface, Gaussian shell is how much? It is r. And the center of non-conducting shell and the center of Gaussian surface both are same, it is O, okay. Okay, according to Gauss law, closed integral E ds is equal to q divided by epsilon naught, okay. And see here, these positive charges, okay, which are within the Gaussian surface, they have a direction this way, they are radially outward. If you choose any charge within the Gaussian surface, the direction will be outward, okay. And you observe, my dear students, these positive charge, they have a direction outward, and this outward direction is exactly 90 degree with Gaussian surface. It means if I consider any small surface of Gaussian, that is ds, the area vector will be perpendicular, okay. If I consider any point, any small surface of Gaussian, okay, the area vector will be exactly normal at 90 degree. Therefore electric field and area vector both are in same line, they are at perpendicular to Gaussian surface. Therefore cos theta value is how much? It is 0. Therefore LHS part I can write closed integral E ds is equal to closed integral E ds cos theta, where theta value is how much? It is 0. Therefore cos 0 is 1, and E electric field is constant, therefore it is taken outside, and closed integral ds. And E closed integral ds, it means if I add all these small ds's, I am going to get the total surface, okay, total surface of the shell, and the total surface of the sphere is how much? It is 4 pi r square. What is r? This is small r radius, therefore it is 4 pi r square. Let us call it as equation 1, it as equation 2. And RHS part, please do observe, my dear students, RHS part, okay, charge within the Gaussian surface, charge within Gaussian surface. charge within Gaussian surface. For this, okay, this non-conducting shell has many charges, and we have considered a Gaussian surface within the shell, and this shell has included some of the charges. Okay, and charge within the Gaussian surface, we can write it as charge, that is since it is a volume actually, three-dimensional, therefore I have to write rho, because V. What is rho? Rho is actually volume charge density, and V is what? Volume. These many charges are there in a total volume, I mean total non-conducting shell, but I have considered only Gaussian surface. Within the Gaussian surface, how many charges are there? There are, this is for rho. Rho is equal to what? Rho is equal to Q divided by V, charge per unit volume. Therefore it is Q, and V volume. V volume is what? 4 by 3 pi r cube. Okay, and these many charges are there in Gaussian surface. In how much volume? It is 4 by 3 pi r cube. Okay, so these are total number of charges, but in Gaussian surface these many charges are there. This all is charge within the Gaussian surface. Okay, so 4 by 3 pi is cancelled. What is remaining? Q is remaining, r cube divided by r cube. Q r cube divided by r cube is remaining. Okay, so I will write here, let us call it as equation 3, putting 2 and 3 in 1. So LHS is E into 4 pi r square is equal to RHS is Q r cube divided by r cube. So r cube r square, 1 r is remaining here, therefore E is equal to Q r divided by 4 pi r cube. This is electric field intensity. Okay, I will wash here. See, you can observe here, this electric field intensity is directly proportional to R. Note, E is directly proportional to R. It means within the Gaussian, within the shell, electric field intensity increases with distance. Okay, so this is very important point, because electric field, so far we have discussed, electric field used to decrease as distance increases. Okay, so this is all about electric field intensity. Okay, once again recollect all the three cases, my dear students. First case, E is equal to 1 divided by 4 pi epsilon naught Q divided by r square. This is outside. And second case, E is equal to 1 divided by 4 pi epsilon naught Q divided by r square. This is on surface. And third case, E is equal to QR divided by 4 pi r cube. This is within the shell. Okay, so by using these three cases, okay, we shall draw the graphical representation, graph E versus R. Okay, so first we shall check with a shell only. See here, this distance is R. Okay, and as distance increases beyond the surface, okay, beyond the surface, the electric field go on decreasing. It means electric field increases till the surface. Okay, so electric field is directly proportional to R inside, and on the surface electric field is maximum, and as you go away from the surface, the electric field go on decreasing this way. Electric field is inversely proportional to square of distance. Okay, so this is graphical representation. Actually, this is within the shell, this is on the surface of the shell, and this is outside the shell. We can draw graph also. This is R and this is E. Okay, so if I consider this as center. At the center, see, at the center electric field is 0 because E is equal to QR divided by 4 pi R cube is there. If R is what distance? If R is 0, then electric field is 0. It means at the center electric field is 0. At the center electric field is 0. From the center, if distance increases, electric field is also increasing. Therefore, electric field increasing, it increases till the surface. And on the surface, electric field is maximum. This is max. Okay. And from the surface, if you go away, the electric field go on decreasing this way. This is electric field decreasing. Okay. And on the surface, electric field is maximum. Therefore, this is inside. And this is on surface. And this is outside. Okay. So this is all about electric field intensity due to uniformly charged thin solid sphere.